A vision language model accepts visual input and produces text-based understanding, answers, or structured output. Unlike a text-only language model, it must convert image information into representations the language component can use. Image preprocessing and visual grounding therefore matter alongside language ability. Vision tasks vary widely. A model may perform OCR, recognize objects, describe scenes, count items, read charts, interpret diagrams, analyze screenshots, or answer questions about visible evidence. Strength in one task does not guarantee strength in another. Local evaluation also differs from ordinary chat testing. Image resolution, preprocessing, image token budget, runtime backend, prompt template, quantization, and memory limits can change output. A model that writes excellent prose may still miss small text or invent visual details. One referenced community benchmark tested 23 model variants across 30 images with 3 runs each. Its useful lesson was not one permanent winner. It found different recommendations for different hardware tiers and showed that configuration and stability can change practical results. The best model depends on task, hardware, latency, privacy, expected volume, and tolerance for false or incomplete output. A slower model with a slightly higher score may be wrong for near real-time review, while a compact model may be ideal for a narrow local workflow. Selection is an engineering decision. Define visible evidence the model must extract, acceptable errors, required speed, and human review controls, then test complete configurations on representative images. Model selection begins with a job statement, not a leaderboard. Describe the input, required output, latency, volume, privacy boundary, error cost, and reviewer. A model cannot be judged useful until success is tied to an operational task. CCTV event review may need concise descriptions and reliable identification of visible activity. Document and screenshot analysis may depend on small text OCR and layout. Product inspection may require consistent recognition of a narrow defect under controlled lighting. Charts and diagrams combine perception with reasoning about labels, relationships, and values. Home lab experimentation may favor broad capability and easy setup. Security alerts require conservative output, visible evidence, and human confirmation before consequential action. Batch review can tolerate slower inference if throughput and completion are stable. Near real-time monitoring has stricter latency and concurrency needs. A model that answers one image well may not keep pace with several streams or a large queue. Define representative normal cases, difficult cases, and costly failures. For OCR, specify character accuracy and formatting. For descriptions, define which facts must be present and which unsupported claims are unacceptable. For counting, state the expected range and occlusion conditions. No universal best model exists because use cases value different trade-offs. Shortlist models that fit the task and hardware, then evaluate them locally with the same prompts, runtime conditions, and human-scored criteria. Model weights, visual components, context buffers, image tokens, and runtime overhead all consume memory. Available RAM or unified memory often determines which model and quantization can run without heavy offloading. System RAM still matters when weights or caches spill beyond accelerator memory. NVIDIA GPUs have broad local inference support across many runtimes. AMD support depends more on operating system, backend, and model format. Apple Silicon uses unified memory shared by CPU and GPU, which can make larger models practical, but also means the operating system and applications compete for the same pool. CPU inference is widely available, but may be too slow for larger models or frequent images. A GPU or accelerator improves throughput when the runtime supports it correctly. Measure actual utilization. Unsupported operations can fall back to the CPU and change performance. Hardware tiers such as 4 to 8 GB, 12 to 16 GB, and 24 GB or more are useful planning categories, not permanent model recommendations. Smaller tiers favor compact models and lower quantization. Larger tiers support more capacity, but still need headroom. Larger models can improve some tasks while increasing latency, power, and failure risk under memory pressure. Concurrency and image size can matter more than a single prompt benchmark. Shortlist configurations that fit comfortably, then test speed, memory, temperature, power, and completion under representative load. The right size is the smallest configuration that meets quality and reliability needs with operational headroom. Quantization stores model values at reduced precision to lower memory use and often improve practical speed. Labels such as Q4, Q5, and Q8 describe broad precision families, though exact methods vary. Lower precision fits smaller hardware, but can affect output quality differently across models. Higher precision is not automatically better in an operational test. The referenced benchmark observed that Q8 did not always outperform Q4 for every model. A larger quantization may consume more memory, reduce headroom, and trigger slower offloading without delivering a meaningful quality gain. Image token budgets and preprocessing settings affect how much visual detail reaches the model. Too little visual capacity may lose small text or objects. More tokens increase memory and latency and may not help if the source image is poor. Batch size, prompt processing settings, context length, GPU offload, thread count, and cache choices also change performance. Compare models under documented settings rather than treating the model name as the whole configuration. Local runners such as llama.cpp, Allama, LM Studio, and other tools may use different backends, model files, prompts templates, defaults, and vision adapters. Runtime version can alter speed, compatibility, and output. Test a small matrix of sensible settings, record memory and completion, and keep one reproducible configuration per candidate. Choose the lowest cost setting that meets task quality and stability rather than assuming the largest file is safest. Raw answer quality is only one selection dimension. A model that sometimes scores highly but frequently times out, returns an empty response, violates the requested format, or changes answers across runs may be a poor operational choice. Visual hallucination occurs when the model describes something not supported by the image. Counting errors may come from overlap, repeated patterns, or weak spatial tracking. OCR errors include substitutions, omissions, invented text, and incorrect reading order. Measure completion rate, latency distribution, memory failures, malformed output, and consistency across repeated runs. 3 or more runs can reveal instability hidden by a single successful example. Keep generation settings fixed during comparison. Use a rubric that separates perception from explanation. Score whether visible facts were extracted correctly, then whether reasoning from those facts was sound. A polished answer should not receive credit for unsupported details. Operational reliability may favor a slightly lower scoring model that is faster, finishes consistently, and stays within memory. The right trade-off depends on whether work is interactive, batch, or near real time and how costly misses and false claims are. Test structured output if automation depends on it, but retain human review for consequential decisions. Select using average quality, worst-case behavior, completion, and resource stability, not the single most impressive response. Thinking mode asks a model to produce or use a longer reasoning process before the final answer. That can help some language problems, but perception-heavy tasks first require accurate grounding in the pixels. More reasoning cannot recover text or objects the visual stage failed to capture. The reference benchmark found that thinking mode could hurt some vision tasks through added latency, instability, or language reasoning that drifted away from visible evidence. Treat that as a testable observation, not a permanent rule for every model. For direct OCR, object listing, simple description, or routine event classification, start with thinking disabled when the model supports that option. This can reduce output length and improve throughput. Compare accuracy and completion rather than assuming shorter is better. Reasoning may help after perception for charts, diagrams, multi-step visual questions, or combining several extracted facts. A useful workflow separates the steps. First, report visible evidence, then reason from the reported evidence. Prompts should ask the model to state uncertainty and avoid unsupported claims. Review whether the explanation cites visible labels, positions, values, or objects. Fluent internal reasoning is not verification. Benchmark both modes with the same images and scoring. Measure grounding accuracy, latency, completion, consistency, and resource use. Enable thinking only when it produces a repeatable benefit for the actual task and hardware. Build a small image set from the actual use case. Include ordinary examples, difficult examples, and costly edge cases. For CCTV review, vary lighting, distance, occlusion, and harmless activity. For OCR, vary font size, layout, blur, and contrast. Create expected answers or a scoring rubric before comparing models. Score factual visual grounding, task completion, unsupported claims, format, and usefulness. Keep human scoring consistent and preserve examples that expose important failure modes. Run each configuration repeatedly. Measure accuracy, completion rate, latency, throughput, memory, power where relevant, and consistency. Separate cold start time from steady inference and record failures or empty outputs rather than excluding them. Control variables. Record model and vision adapter versions, quantization, runner, backend, prompt template, image settings, context, thinking mode, generation parameters, and hardware. A result without configuration detail cannot guide deployment reliably. Use generic public benchmarks as background, not as a substitute for local evidence. The 23 model, 30 image, 3 run benchmark illustrates tiered selection and repeat testing, but rankings will age as models and runtimes change. Maintain an evaluation log with dates, results, decisions, and rejected alternatives. Rerun the suite after model, quantization, runtime, driver, prompt, or hardware changes. The benchmark is a living acceptance test for the workflow. Local processing can keep images and outputs under direct control, but deployment still needs a data policy. Define storage, retention, access, export, logs, and deletion. Avoid sending images to external services unless that flow is approved and transparent. Review the model and runtime licenses for the intended use, distribution, and modification. Track model source, file integrity, version, prompt template, and dependencies. Treat model updates as software changes with regression testing. Operational workflows need queues, timeouts, retries, alert routing, and human review. A fallback model or simpler pipeline can preserve service when the preferred model exceeds memory or fails, but the system should label changed capability. Cost includes hardware, power, cooling, storage, administration, and reviewer time. A larger model may cost more operationally without improving the task. Monitor throughput, completion, latency, memory pressure, temperature, queue depth, and output quality. Do not blindly trust model output. Important decisions should link back to visible evidence and accountable review. Local vision systems should not be used for covert stalking, harassment, inappropriate surveillance, or identifying private individuals without lawful authority. Reevaluate over time as cameras, documents, use cases, models, drivers, and runtimes change. Keep a known good configuration and rollback path. Deployment success means stable, privacy-conscious assistance that remains understandable when the model is wrong or unavailable. Choosing a local vision model is an engineering decision, not a popularity contest. Vision language models differ across OCR, objects, counting, charts, screenshots, descriptions, and visual question answering. The use case defines which differences matter. Hardware fit includes VRAM or unified memory, system RAM, accelerator support, concurrency, and operational headroom. Model size, quantization, image token budget, runtime, prompts template, and thinking mode form one tested configuration. Accuracy must be considered with completion, latency, memory failures, hallucinations, OCR and counting errors, and consistency across repeated runs. A smaller or lower scoring model can be better when it is stable and fast enough for the workflow. Benchmark locally using representative images, pre-written rubrics, repeated runs, controlled settings, and a durable evaluation log. Community benchmarks provide hypotheses and hardware tiers, not permanent answers. Deployment adds privacy, licensing, retention, cost, power, monitoring, fallback, updates, and human review. Keep important decisions grounded in visible evidence. The best model is the configuration that meets task quality and reliability on available hardware while preserving privacy and accountable human judgment.